The hypothesis of the universe's eventual heat death, also known as the Big Chill or Big Freeze, has emerged as the leading theory concerning the ultimate fate of the universe, depicting an eventual state of no thermodynamic free energy, incapable of sustaining processes that increase entropy. The heat death theory implies not a particular temperature, but the cessation of work due to the lack of temperature differences or other exploitable processes. Should the universe's curvature be hyperbolic or flat? Or should dark energy function as a positive cosmological constant? An enduring universe expansion, culminating in a heat death, is anticipated. Over a vast span of time, a steady cooling leads the universe to a low-temperature equilibrium. Lord Kelvin is credited with the initial ideation of heat death in the 1850s, taking the theory of heat as mechanical energy loss in nature, as encapsulated in the first two laws of thermodynamics. Kelvin extrapolated these principles to universal processes. This also led Kelvin to develop the heat-death paradox, which negates the possibility of an infinitely old universe. The hypothesis of heat death is anchored in the second law of thermodynamics, stating that entropy tends to rise in an isolated system. Therefore, if the universe exists for a prolonged period, it is destined to approach a state where all energy is uniformly distributed. In other words, there's a natural propensity for the transformation of mechanical energy into thermal energy, leading to the mechanical motion of the universe grinding to a halt as work turns to heat, complying with the second law. The concept of universal cooling, eventually resulting in a universe too cold to support life, originated with the French astronomer Jean-Sylvain Bailly in 1777. He theorized that planets have an internal heat, undergoing various cooling stages. For instance, Jupiter is in a stage too hot for life for thousands of years, while the Moon is too cold. Bailly envisioned a final state of equilibrium, where all motion ceases. To sum it up, Lord Kelvin in 1851, building upon the views of Sadi Carnot, James Joule, and Rudolf Clausius, was the first to loosely propose the idea of heat death resulting from the laws of thermodynamics. His viewpoint was then built upon over the next decade by Hermann von Helmholtz and William Rankine. Thomson, in his 1862 work on the age of the sun's heat, explored the endless cycle of energy transformation in the universe, reasserting his staunch belief in the unending existence of energy and its ceaseless dispersion. Thomson argued against the idea of the universe as a finite entity winding down towards a state of total stagnation and death. Instead, he envisioned a limitless universe continuously transforming potential energy into discernible motion and heat. Thomson questioned whether the universe would ultimately reach a state of thermodynamic equilibrium, highlighting the uncertainty with the analogy of a clock. He hypothesized that overturning this direction and rejuvenating the universe would necessitate a powerful act akin to creation. Thomson's theories also introduced what's known as the paradox of heat death, Kelvin's paradox, defying the classical notion of a universe with infinite age. According to him, the universe has yet to reach thermodynamic equilibrium, implying that further work and increased entropy are possible, with the existence of stars and temperature disparities serving as physical evidence of a non-eternally old universe. In the years that followed Thomson's thought-provoking papers of 1852 and 1862, fellow scientists Helmholtz and Rankine acknowledged Thomson's theories while exploring the concept's depth. They claimed that Thomson had suggested a heat death, a cessation of all physical phenomena, as the universe's eventual end. Speculation about the universe's final state varies, hinging on assumptions made about its ultimate destiny. In the late 20th and early 21st century, theories proposed for an infinitely expanding open or flat universe estimated either a heat death or a big rip. Assumptions of a zero cosmological constant envisioned a universe gradually cooling towards absolute zero. Alternatively, with a positive cosmological constant, the universe's temperature would level out at a non-zero positive value, leading to a state of maximum entropy, precluding any more work. As the universe progresses, its activity is expected to significantly decrease due to a thinning matter, resulting in exceptionally low energy levels that span unimaginably long timescales. There exists the possibility of a second inflationary stage, or the decline of the current false vacuum into a state of lower energy. Furthermore, there is the potential for the universe to reach a point of heat death, effectively ceasing entropy production. Over immense time periods and through phenomena like Poincare recurrence theorem along with thermal and fluctuation theorem, it is proposed that there could come an instance of spontaneous entropy reduction. This could spur the creation of another universe through random quantum fluctuations or quantum tunneling. The concept of the entropy of the universe is contested, as Max Planck argued that it lacks a clear definition. Several scientists and authors have raised questions about applying the notion of entropy to the universe, considering it to be presumptuous and baseless due to the lack of equilibrium in the system. These critics argue that the concept of entropy is not universally acknowledged for systems outside of equilibrium even when in a stationary state. A study conducted in 2010 states that the entropy of a standard gravitational field remains unknown, making it difficult to determine gravitational entropy. This research led to the suggestion that the universe's overall entropy may be higher than previously thought, with supermassive black holes being the leading contributors. Scientist Lee Smolin expounded on this notion, suggesting that gravity's known importance in maintaining the universe from achieving thermal equilibrium reinforces the belief that such a system would not evolve towards a homogeneous state of equilibrium. Instead, it could grow to become increasingly structured and heterogeneous, breaking down into varied subsystems. This perspective was strengthened by a recent experiment revealing a stable, non-equilibrium steady state in a relatively basic closed system. In summary, an isolated system that has been broken down into subsystems may not necessarily reach a state of thermodynamic equilibrium, but instead exist in a consistent non-equilibrium state. Although entropy may transfer between these subsystems, its generation would be null, a notion that doesn't conflict with the second law of thermodynamics. In the 1981 episode of Doctor Who, Logopolis, the narrative centers around the heroic doctor who discovers that the Logopolitans, in an effort to prevent the end of our universe, have ingeniously created vents known as charged vacuum emboîtements, CVs, to discharge heat buildup into alternate universes. This sci-fi theme is echoed in the 1995 computer game I Have No Mouth. And I Must Scream It reveals that a vicious supercomputer named him remains safe from the universal heat death, mercilessly tormenting its undying victims forever. The universe's heat death notion is explored again in the 2011 anime series, Puella Magi Madoka Magica, where the primary antagonist, an alien named Kyubey, admits to mass, producing magical girls to harvest energy, countering entropy, and the eventual universal heat death. Endwalker, the concluding scenario of Final Fantasy Exiv, presents a despair-driven alien race, Ea, who have given up on life after becoming aware of the inescapable heat death of the universe that makes everything else futile. The universal heat death concept is also the overarching theme of the Exili sequence series, where Photino birds are making an effort to expedite the universe's extinction by increasing the pace at which stars evolve into white dwarfs.